with all the states allowed to be inserted. Okay, so let me do more precisely the following thing. Let me choose a physical state on the as a final state, psi phys, and then I do any calculation I want, and choose the initial state here to be an arbitrary down state. By an arbitrary down state, I mean a state which has any value of k, not necessarily the k value such that k squared plus n squared is equal to 0, some arbitrary down state. Okay? Now, because this state was exact for every value of k for which k squared plus n squared is not equal to 0, but every such calculation would be 0 for those k's that were not equal, that were not k squared plus n squared equals 0. Okay? And therefore, if we did a calculation of this form, we get an answer that was proportional to a delta function. To at best be proportional to a delta function. Now, if you see, in the situation of the point particle, unlike in string theory, you can actually use this formalism to do off-shell calculations. Okay? You can actually use this formalism to do calculations of correlation functions of operators that are not just S matrix elements, because this is calculating field theory. That you can actually do. And it's a property of field theory, okay, that all correlation functions of operators have certain reasonable analytic properties. In K-space, you have poles and cuts and various other structures, but you never have delta functions like this. This kind of analytic behavior in field theory correlators is just never present. In fact, the general theorems about the analytic structure of operators in local quantum field theory, which disallows a singular behavior. Okay, so if you were to treat these states seriously, it doesn't. Correct. If you were to treat these states seriously, they don't suffer from the problem that that you get an ambiguity if you change the choice of gauge fixing. That's not the problem, yeah? The problem is that their amplitudes are, you would get answers for amplitudes that were very singular, that were not the answers that are allowed by general rules of quantum field theory. Okay? So we're in a situation where what has happened? We know that we've got twice the space. We know that we've got twice the physical space in question. We know because we've done 4 different methods of quantizing the theory, all of which are much more physical than this. And we know the derivative spaces. We've done this BRST quantization, we've got twice this physical derivative space. So one of the two must be disallowed. One of these has the strange property that if you use it to do calculations, you get answers that are of the form that are just not consistent with any sort of field theory behavior. Okay? So what we'll do is just be pragmatic. We'll throw away this guy. When we say the physical state of our system, the physical states of our system consist of up times k. Okay. So I know this is not terribly satisfactory. I know this is not terribly satisfactory because it's not, some systematic procedure we've used which works out around to the end to give you the answer. But that's basically really the way physics is. What was the logic behind this BRST quantization? This BRST prescription that this was physically derivative space? It seems reasonable. Right? It seems like property V1, this is a property. But here in this situation we've got a subset of states that had all those reasonableness requirements. That's also a reasonable thing to do. And it agrees with the right answer. The right answer meaning the answer that we get by other means of quantization. Okay? So, there may be a more formal way to understand why these states are, not good states. But we're just going to be pragmatic. We're going to say that if we were to do a BRST quantization of this point particle, we would do it by throwing out these states. Okay, we would just by hand say that physical states are states that are annihilated by this was the one annihilated by so B on psi phys is equal to 0. So the end result of this whole procedure is a prescription. that for the point particle, physical states obey, the cohomology of QPRST plus obey the extra condition B on side physics. How do we know this is the right answer? Well, at least this gives us the right spectrum. We know the right answer to the spectrum is, we've done in many different ways. And it's also these states that will give us reasonable answers for correlation functions. Answers that match not just what we know to be correct. In some cases we know what is correct because we put in the right interactions with these point particles. We haven't discussed by the way how to do interact with point particles. Just an interesting problem which we won't get to in this format. We won't get to in this course. It reproduces the final diagrams of quantum field theory.
Okay, so the states we are throwing out are the states down K, the K square is actually
right. The states that would have been exact, that were exact everywhere else, okay, but not exactly at K square equal things. K square plus M square, those states.
Okay, can you understand this way some kind of an I-epsilon description? Okay, I have somehow slightly out
here. You see, maybe what you're saying is rewording what I said. The I epsilon prescription assumes that you've got reasonable analytic behavior. These are things that are exactly zero, except at K squared plus M squared. So even to put this in the language of quantum field theory, you wouldn't be able to do it. Now, these states just don't exist. It's a little bit of shit. Or they don't exist in the sense that they give you zero correlation, zero amplitude with any physical process. Exact. Even a little bit of shit. So, all of the language of field theory, like an I-epsilon, would apply to these states.
No, I mean, we can think of adding an imaginary part to Mars. And then you can, K square, if it is always this thing, it will never be, K square plus M square will never be zero. So anyway, all this is exact.
I see what you're saying. But yeah, maybe you could say it that way. I'm not sure. Okay, please.
If you do that, won't it spoil the first one? I mean, if we add a I-epsilon to the mass, we'll be throwing out the down states, of course, but then what will happen to the up states?
So up states will have that K square plus M square equals
slightly modified on-shell relationship. I mean, I don't know. I think the way to treat that is just pragmatic. In a situation where you can solve the theory in two different ways. One way is certainly correct. The second way was some ansatz. You know what the right answer is. You must do what you see, what are we doing? We've got this enhanced Hilbert space that was not physical. Okay? And we want to find a way of cutting it down to the physical Hilbert space. We had a criterion from this BRST procedure, which was that whatever states we have must be in BRST cohomology. But we have no guarantee that space itself would not be bigger than the physical Hilbert space of interest. There was no guarantee anywhere. Again, we saw that in this case it is bigger. Okay? Now we want to do the extra cutting down that will get us our answers. We want to kill half of the states. We see we have basically two options. We want to get rid of either this and this. Of course, it could be linear combination. Okay? And we see that these states have very funny properties. We just throw them away.
Okay. Generally, you can't do that because they use
I completely agree. So it's
not obvious that.
But at the level of a free theory,
Apart from right.
At the level of the free theory, all we want is the Hilbert space. The question will be when you get to an interactive theory. When you use this to generate interactions, then is it a consistent thing to do? For instance, to states of the first sort that you keep, would they try to mix with states of this sort? Would they try to produce these interactions? That's a very good question. That kind of thing we will have to address carefully in any situation where we use this. Okay, now the reason I've done this point particle so much in detail is that we're going to do something very similar to string theory. Okay, so in string theory we will do a BRST quantization of our action, and we will put two conditions on physical states. The conditions will be first that they belong to BRST cohomology, and second that they be annihilated by the zero mode of the B field. Namely, the second condition will be B0 and field is equal to 0. For more or less the same reason as this. Now, when we use this in string theory, we will perform a careful analysis of, for instance, issues like are states that are not annihilated by being produced and produced and so on. There we will be very careful. When we use it to study interactions. At the level of the free theory, of course, we will justify this more or less for the same reasons as here, but also again by a comparison with another way of computing the spectrum, the way we've already done in class. It's light code. We have to get the same answer. Once again, we find double answer. Okay, so my answer to your question is that it's an ansatz, and one that we will be very careful to check for consistency. But I haven't seen a careful, principled analysis of this ansatz beyond analytic properties, which we're working on. Okay, I think we should stop this class here apart from questions or comments. Okay, so what have we done in this class? Let me just summarize. What we did was to understand the BRST procedure in generality. We understood how you can in general construct a BRST charge, blah blah blah. And then we applied this to the point particle. Okay, we applied this to the point particle with that one extra prescription that was put in by hand, namely that the physical states, in addition to BRST cohomology, being BRST cohomology annihilated by B, with one extra prescription, we recovered the Hilbert space that we know to be correct. Okay. Now, in the next class, what we're going to do is to extend this analysis to string theory. Okay, we're going to write down the BRST charge on the worksheet of the string, and then in the next class we will begin a careful analysis of BRST cohomology of string theory, and the BRST cohomology together with this condition of B0 and states of string theory. What we will do is to prove what's called the no-host theorem of string theory. That is, we will prove that this cohomology coincides with the Hilbert space that we obtained through light code quantization in a previous class. Okay, this plus one or two more lectures will end the initial formal development of string theory, which is essentially the boring part of the study of string theory. There's all this formalism we have to get through. Soon after that, we will start using this. We will start calculating scattering amplitude. We try to do physics with this. That will be in about 3 lectures. Okay, so just again about schedules, we will have one more class this Friday, and then the next class will be on something like the 30th of December, the Wednesday of January. Okay.